Hey guys, ready for action?
Certainly then.
Should have like a light switch up here where there's very lights out there. Makes you good at elementary school. Get quiet.
Oh, they would do that on lunch break. They would shut it off, and everybody
Time to
would
get quiet.
You can have like stage lights. Everything else cuts off.
Hey guys, come on. So, any questions from last night? Anyone? Speak now, forever holds peace. We good?
Wait, what? We just asked them on the review day.
I don't know if we're gonna have a review day. I said we're not having a review sheet. What's the point of a review day?
Could you do a homework problem?
If you'd like, yeah.
Can you do 31? Oh, that's what that said. It was like 31.
If you tell me what 31 is.
It's, I took that as
A lot going on. You ready?
Yep.
a.
Can't hear if y'all talk.
The 3x4 matrices on the top row.
Matrix.
Matrix, excuse me. Sorry.
Yep.
1, 1, 4, -1. 3, 8, 10, 3. -2, 1, 12, 6. And then there's another one.
Okay. What's the other one?
1, 1.
Again, a 3x4.
Yeah.
What are you doing with these?
There's 3.
It's
But what are
filling
you
the blanks
doing?
To the elementary round.
Oh.
Yeah.
I'm not going to ask you to do the fill in the blank thing. So as long as you can get there to the very end, you're fine.
I think it's the second one. I have no idea.
So what was the directions were to fill in the blanks to get it to what?
It was like, I don't know.
What number? Okay, so they were basically trying to get, they were asking you what operations will get you to this point. I'm not going to ask you that. I'll just say, put this in row echelon form, maybe, which means you do the same thing you did last chapter. I want 3 zeros. The only extra thing in addition to those 3 zeros would be to what? What? You need ones, right? That's row echelon form. I am not going to ask you to manually put it in reduced row echelon form. That would mean zeros there, 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 and there, there, and there. I'll leave that to a coding theory class. To me, it's a waste of time when you can do back substitution like we learned. It's a lot of effort to get 3 more zeros. It's not a lot of effort to plug X, Y, Z's and Y's back in. So the first thing, how can I make those zeros? If it were me, I'd multiply the top by a -3. Add it to this. And that makes that 0, 5, -2, 0. 0, 5, -2, 0. And then I would basically go back to that blue line and say, I don't need that. I could divide by -3, get back to where I was. Then I would take this top row and multiply it by a 2. And add it to the bottom row. That gives me 0, 3, 24. 0, 3, 24. And at that point, again, I would go back and divide by a 2 to get back to where I originally was, which was 1, 1, 4, -1. At this point, I'm just going to bring over my 1, 1, 4, -1. And that's my first, that's usually what I do in the first step. Okay, then I'm done with this top row, because if I use this top row with any of these, I'm going to get rid of my 0 because it's going to put a 1 and a 0 or 1 and a 0, and it's going to change my zeros. So at this point, I'm just using these 2. So to make that number a 0, I'm going to come in here and multiply that by a 3. And that by a -5. And then add those 2 together. And when I do that, I'll put it here. I get 0, 0, -106. Unless I've made a careless error, -20. And then I really don't need this red line, so I'm going to divide that back by 3 and keep 0, 5, -2, 0, and 1, 1, 4, -1. So at this point, I have it in what I was doing last chapter with the equations. But if I wanted row echelon form, if I wanted that form, I need leading ones. So I guess at this point, if I really did want that form, the top is fine because it has a 1. This I would have to divide by 5. And then this I would have to divide by -106. And that would give me -20, which is what? 10 over 53. And that would be row echelon form. So that maybe is a question I'd ask. So if you were looking at that and like bothered by, wait a minute, what step do I use? I thought I was making it easy on you by just doing that where you didn't have to go to the bitter end. You could just go, hey, what would I do to make both of those zeros? But if it bothers you, don't worry about it. As long as nobody's going to ask that question. That was kind of like baby steps. So if the baby steps confused you, hey, but you can still do this, you're fine. Y'all with me? Okay. So literally, you would have rather done this? No, you like this baby steps? Like, yeah, I thought you would like that better too, just having to do, like if they said, hey, what would these numbers be if those were zeros? I think that was kind of what it was asking. Or what would these numbers right here be if those were zeros? That's kind of what they were saying is, hey, make these zeros and then just fill them in. But again, whatever. As long as you understand the process to get to here, or even to here, if I just said solve manually, if it were me, I would get to here, right? And then from here, what do I know? -106, whatever that variable is, call it Z, call it C if you want to go ABC. It's saying that Z would be 10 53rds. And then from there, you should be able to plug 10 53rds into this. This is essentially what? 5y minus 2z equals 0. Plug that there and solve for y. Plug both of those in there for y and z and solve for x. But if all I did was say get it in this form, that's what you want to do. And again, I won't ask you for reduced row echelon form unless I give you your calculator. And if I give you your calculator, just RREF this thing, and it'll jump you right to whatever that thing is that has zeros above and below the ones. All right, anybody else on the homework? Okay, today is just going to be a quick review, kind of a nice way to end the week. All right, a quick review of what we already learned from last year. If you didn't learn it last year, then pay attention and ask good questions. But we're going to just review some of the operations like inverses, multiplying, adding, scalar multiplication, just some basic stuff. Talk about the commutative property with multiplication and what is implied or not implied there. So let's take a look at that. And guys, please feel free to ask questions, especially if you were not with me last year. I don't know exactly what you guys learned. So if there's something in here that you didn't or you're rusty with, ask questions. Y'all are real chatty. Come on, focus. Yeah, I know. It's not Pozo today.
Yeah, she's just such
Too many sugar in your muffins. Getting all hyper right here. Okay, right here, guys. First thing I want to talk about is just scalar multiplication. We call a scalar number. Normally, you don't walk around talking scalar number. Like if I go, how old are you? And you go 17, I'm like, ooh, scalar number. Like we don't do that, right? But all the numbers we deal with are scalar numbers. But those are matrices. Matrices are like a compilation of scalar numbers in their rows and columns. But this outside number is a scalar. A scalar, and let's hear this, when you multiply a scalar into a matrix, you multiply it by everything. If you ever multiply it into a determinant, you do not multiply it into everything. You multiply it into a what? One. So if you have a determinant and a scalar, first of all, I would never multiply a scalar into a determinant. Why would I want, you remember what a determinant is? Where you have to do the diagonal method or expansion by minors, whatever. Why would I want to multiply a number in? It just makes the numbers in there bigger and makes it harder to do the determinant. If it were me, I would evaluate the determinant, then multiply it. But you can. So if I did, I multiply it into either what? One row or one column. That's how you multiply the determinants, which are always square. This is not a determinant, right? You see the little brackets on them? These are matrices. You don't evaluate them. They just represent something. They might represent an equation. They might represent just something from a spreadsheet. Who knows? But right here, this -2, because that is a matrix, has to go into everything. So when that happens, you get -6, +4, -8, 0, -1, -10. And that +5, and by the way, even if it was a -5, I'm going to still multiply whatever that number is in, and then just leave a plus in its place. So even if that was like right here, I multiplied the -2 in, now there's basically just a +1 on the outside. To me, I like doing that. I would not, if that was a -5, I would not multiply a 5 in and leave a negative, because then I have to sometimes go negative minus negative, negative minus positives. It's just one extra thing I have to do mentally. So I'm always going to multiply the entire thing in and just put a plus outside. Don't turn it into multiplication when you multiply it. So that gives me a 40, a -5, 0. It gives me a -15, a -20, 30. And now that there's a plus, I can ignore this one. It's not really doing anything. Right here, I can go, all right, that plus that, that plus that, that plus that, that plus that. And I don't think you're going to have much trouble with this, other than with the exception of maybe some careless errors that hopefully you can cut down in when you check your answers. And again, if it's a matrix, I can't evaluate those. They're just sitting there. All right. And by the way, you can't evaluate. Determinants are always like 2x2s, 3x3s, 4x4s. If you're going to evaluate, they have to be square looking, not rectangular. Now, when it comes to multiplication, it's different. You don't, like with addition right here, where you, like with addition, you add these two, add these two. These are called adding corresponding elements. So with addition, you add corresponding elements. With multiplication, you don't do that. Do you remember what you do with multiplication? Yeah, you're going to be looking at the rows of this, and you're going to be kind of pairing them with the columns of this. It's always rows, columns. In the olden days, we would remember that because of RC Cola, but a lot of you don't even know what RC Cola is. RC Cola was like Coke in the South back in the day. You go into country stores and they'd have RC Cola and a moon pie. You know, that would be like staple. But anyway, so we used to say RC Cola. It's always RC, not columns, rows. Now, if the number of elements in the row doesn't match the number of elements in the columns, you can't multiply. So you, even if sometimes, like right here, these were the same size, right? Well, if this was multiplication, you couldn't do it because the number of elements in that row don't match the number of elements in this column. So if this had been a times right there, you wouldn't have been able to multiply. Like right here on number 3, you can't multiply these because you can see the number of elements in these rows doesn't match the number of elements in these columns. So you cannot multiply here. So if it says multiply, just say I can't. But make sure you can, right? Every year I have somebody do this. They come in here and they go, I'll give them one that they can multiply like this. And they come in here and they go, all right. Oh, don't match, can't multiply, right? Don't do that, right? It's not columns, rows, it's rows, columns. So let's just say that I circle my rows and my columns. Oh, another way you can do it is, if you look at the size of this, what do we call the dimensions of that? This has what? 3 rows and 2 columns. This has 2 rows and 2 columns. So if you write down the dimensions, you can multiply if the 2 inside numbers match. You can multiply. And the 2 inside numbers stand for the 2 numbers that are in each row, the 2 numbers that are in each column. Now, what you end up with is that. So I'm going to end up with a 3x2, which means I'm going to end up with 3 rows and 2 columns. So if I think about this right here, I'm going to, and you don't have to draw this, but I'm going to basically end up with 3 rows, 1, 2, 3, 2 columns. So there's 6 numbers I'm looking for. So how do I do this? I take the first row and the first column, and I'm going to pair them together, kind of like you read left to right, top to bottom. So I'm going to pair those together and multiply and get a 3. Then I'm going to pair those together and multiply and get a negative 12. And then I add the result. So I add the 3 and the negative 12, I get a negative 9. That goes there. And why does it go there? Because that is in the first row, first column, and I use the first row, first column to get those numbers. Now, for the next column, I'm using first row, second column. So I put it in the first row, second column space. And what does that give me? Negative 2, positive 3, positive 1 when I add them together. And I just keep doing this. Now I go to the second row, first column, and I'm going to put my answer in the second row, first column spot. So negative 12, positive 8, negative 4. Next one, positive 8, negative 2, positive 6. Then down to the bottom row, negative 15 and nothing. Love the 0 in there. 10 and nothing. And that's how you multiply matrices. And again, you can do this little thing if you want to see if you can. Remember, you can if the numbers inside match. The nice thing about checking this is right here, the numbers on the outside show me what I end up with, a 3x2 matrix. But some people like just looking at, like right here, they just like going, all right, I'm gonna circle the rows and the columns. Like I come in here and go, all right, rows of this, columns of this, and they go, oh wait, these don't like, I don't have something to match with the 5, so can't multiply. The only downside of this is what size do you end up with? So I guess you could look at it and go, well, when I pair these, like, well, I don't end up with anything here. I guess the downside with just circling like we did here and not writing 3x2, 2x2 is just make sure you understand, okay, what am I going to end up doing here? I'm going to end up going this times this and this times this, this times this and this times this, this times this and this times this. Oh, well, if I have, I guess you could think if I have 3 rows circled, I'm going to have 3 rows. If I have 2 columns circled, I'm going to have 2 columns. So that tells me I'm going to have that. So whatever you do, whatever plan you have a plan when you multiply. Because to me, these are the easiest problems, some of the easier ones on the test. If you know what you're doing, you just got to be careful about careless errors because there are a lot of little mini calculations you make. Now, right here, what does it look like is, ignore the directions for a second. What does it look like I'm trying to check here? Yeah, it looks like I just took these two and switched them, didn't I? That went here and that went here. So what property is, well, that times that equals that times that? Commutative. Commutative. Okay, so the commutative property says A times B equals B times A. And that is a property in algebra that we can use. It works with algebraic numbers that are scalars. It does not work with matrices. Now, it might work occasionally, but to be a property or like a theorem, it has to work all the time. And it does not work all the time. And you can see that real quickly here. You can see that real quickly. I mean, you don't even have to do the whole thing, right? If you just, this is a 2x2 and a 2x2, so I'm going to end up with a 2x2. That's a 2x2 and a 2x2, so I'm going to end up with a 2x2. And all I have to do is really just check the first place, and I can see that these don't match. Look, 6 and negative 6, that would have a 0 there. And if I jump over here, 6 and negative 4, that would have a 2 there. So clearly these aren't equal, even before I go check all the other numbers. So this is an extremely important concept when it comes to solving equations that have matrices in them, because you guys use the commutative property when you're not even thinking about it. Let me give you an example. If I said solve right here, tell me exactly what you would do if you couldn't divide, because we can't divide with matrices. So just using multiplication, what would you do?
Multiply by 1/2.
Okay, tell me exactly. Where are you going to put 1/2 here?
In front of 2.
You probably put it right there because you don't want to rewrite the problem, right? And where would you probably put it here? You'd probably put it here because most of the time that equal is so close you don't have room, right? You just did the commutative property and you don't even know it. Because if these things are equal, then that right here, if it is equal, that's like you saying, hey, these are equal. A equals A. You're kind of saying that. And then you turn around and go, well, I'm going to multiply B on this side and B on this side. You literally used the commutative property and you didn't even think about it. Well, if I do the same thing with a matrix, like for instance, let's just say I had a matrix problem like this. Say I had 2, -1, 3, 4 times x equal 5, 2, -1, 7. Okay? And I said, hey, this is true, but solve for x. This is like me saying, hey, A equals A. So if you came around and you're like, well, I got to solve for x, so I got to get rid of that, just like I got rid of the 2 a couple seconds ago, right? So because we can't divide, we multiply by a reciprocal. Well, we don't call it a reciprocal in matrices. We call it an inverse. We call it an inverse because what is a reciprocal? It's a multiplicative inverse, right? So we call it just an inverse here, but we always come in, if we're sloppy and lazy, we go, oh, inverse, multiply the inverse, because you got to figure that out, which we will by the end of the day. And then you come up over here and multiply the inverse. And if you do that, essentially, you just multiplied by B on that side and B on that side, and you just demonstrated the what? The commutative property, which does not work with matrices. So in this case, what do you have to do to make this work? You got to put it in here, which means you are going to have to rewrite it, put it there, and put it there. But if you don't, you won't know you missed it. You'll still come up with an answer, and you'll never know you're wrong unless you went back to the original problem and checked your answer in there to see if it gave you that, which nobody does. I mean, I can't say nobody. Very few people do, because you're like, oh, I'm good. Time to move on. And then you miss it badly. And that's the main thing I'm checking on this is, did you know to do that? And did you know how to find the inverse? So if you put the inverse out here, I'm like, and the only reason you'd even get a dot's worth of points is if you got the inverse correct, which we'll talk about in a second. So this commutative property is a big deal here. Make sure you don't assume that when you're dealing with matrices. If you're dealing with anything else, great. It is a property. All right, what about this? Multiply. So what size, if you're thinking this route, circle the rows, circle the columns, right? So if this is rows and columns, what am I going to end up with?
4 by 4. 2 by 4.
Let's see. This is a 2 by 4. This is a 4 by 2. So yes, I can, 4 by 3. So yes, I can multiply, but I end up with a 2 by 3. And again, what you could also do is, well, I circled 2 rows and 3 columns. So I'm going to end up with a 2-row, 3-column matrix. So if you thought about it this way, 2 rows, 3 columns, I've got to figure out the numbers that go in there. And I'd rather you not put like the green little whatever's in there, but I'm just doing that to help you see. So what do? Carefully, 0, 0, -6, 2. That gives me a -4 when I add those together. Next row column, 3, 0, 0, -4. It gives me -1. Next row column, 1, 0, -3, 0. Gives me -2. Next row down, 0, -5, -2, 0, -7. Next row column, 12, 10, 0, 0, 22. Next row column, 4, 0, -1, 0, +3. And maybe double check your work. If you're not very visual or those numbers, you'll notice I put a lot of zeros to kind of help you out. I don't think there was a single time I had to actually add more than 2 numbers there. But sometimes you do end up adding 3 or 4. If that's the case, then do something like if you need help, go, all right, that's a 0, that's a -5, that's a -2, that's a 0, okay, -7. I mean, take your time, whatever you need to do, but make sure you can get these as accurately as possible. Because usually every time you miss something, I dot you. And keep in mind, we basically made what? 24 little calculations? No, we did that more than that because we also added. So a lot of calculations. All right, what about this? Move back up. If that's A and that's A inverse, if it was, what do you know about A times its inverse? It's going to give you the identity, right? That's what an inverse does. A multiplicative inverse gives you the identity element. The identity element in addition is like 3 and -3. The identity is 0. The identity element and because anytime you add 0, you get what? Itself, right? You keep your identity. If I add nothing to myself, I'm still myself, right? In multiplication, the identity element is 1. And in a scalar world, it is 1. But in a matrix world, it's not 1. It is the what? The identity matrix, which is that matrix that has like a diagonal of 1s with 0s above and below. So if this is a 2 by 2 and that's a 2 by 2, you know a 2 by 2 times a 2 by 2 is a 2 by 2, right? You know that. If this was a 3 by 3 and a 3 by 3, you're going to end up with a 3 by 3. So you basically just check the size and go, well, since these were both 2 by 2s, I know I'm going to end up with a 2 by 2, and any matrix times its identity gives me the identity matrix. Now, I will caution you one way. Every now and then, I will give you a matrix, call it A. All right, let's just say I gave you this. And you might have trouble doing this right now. What if I said, hey, that's A, then what is A times its inverse? And a lot of people go, oh, I know that A times its inverse always gives you the identity. And they come over here and they write 1, 0, 0, 1. And they think they're right, and I count it wrong. Why would that happen? It would happen when a matrix doesn't have an inverse. And sometimes they don't. And you will learn, remember, I don't know if you remember where you like swap the spaces, change the signs, and then put 1 over the determinant out front. The determinant of that ends up being 0. So if I do the inverse and the determinant ends up being 0, then you don't have an inverse. And if I don't have an inverse, I can't possibly get an identity if this thing doesn't even exist. Are you with me? That's a great little ciphering question, great little mathing question, happens all the time. In fact, once I put it on a bonus and I missed it and I made the problem up. Like I looked at the next year, I was like, oh, yeah, I'll check to see if they know that. And I was given, everybody put identity and I was like, +2, +2. And some kid finally comes up and he's like, I don't think the inverse exists. Shouldn't it begin? Oh my gosh, I fooled myself. It's so easy to miss that and get sucked in by that principle. But yes, that is true. How do I know this one is? Because it did exist. And I know it exists because I can see it there. They told me that's what it was. So yeah, I can make that assumption if that's true. But if I didn't give you the inverse, check it. If it does exist, great. And all you got to do to see if it exists is check the determinant. And if you're looking at that and going, how do I know what the determinant is? We haven't talked about that yet. We'll get to it. All right. What about this? What is an identity times anything or anything times an identity? That thing. Because you remember the identity element with like if I'm 54 years old and I multiply myself by the identity 1, I'm still 54. In a matrix, it's the identity is not 1, it's that. But again, what the identity element means is if I ever multiply it by the identity, either on the front or back, doesn't matter, I'm always going to get the actual matrix. And you can see it, look, rows, columns, -3, nothing, bam. 4, nothing, bam. Nothing, 5, bam. Nothing, 7, bam. And it doesn't matter whether it's on the front or the back, the identity. It can be on either spot. Those are actually commutative with identity elements, but not with other stuff. Same thing here, right? The identity times anything is that thing. So right here, you don't have to do the calculations. You see that and know that, of course you can say this. Now, this stuff is a little new, but the process to begin, but the process to solve is not. So this says use an augmented matrix and then Gaussian-Jordan elimination to determine the equation of the parabola going through those 3 points. So, somebody give me an equation of a parabola. No, a generic equation of any parabola. Okay, I'm hearing y minus k equals ax minus h squared, and that is true. But in terms of a function, y equals, is it always 1x squared? Ax squared plus bx plus c. That's a generic equation for a quadratic function, right? And is it still a quadratic function if I don't put the y in front, but I put the y in the back?
Yes.
Still is. In fact, I kind of like it like this because if I'm about to use a matrix, I kind of like the constant on the right side, don't I? Okay, so with that in mind, right here, how could I use these 3 points to help myself solve?
Plug them in and then
Plug them in for what?
X and Y.
Since all of these stand for x's and y's, one at a time, if I plug -2 in there, so this is me plugging -2, 5 in, I would get what? -2 goes in for x, so I get 4a minus 2b plus c equals what? 5. And I have an equation, right? But I could do it again, couldn't I? And plug in 4, -1. And if I plug 4, -1 in, what do I get? 16a plus 4b plus c equals -1. Y'all see what I'm doing? And if I plug 815 in, I get 64a plus 8b plus c equals 15. And now what do I have? I have a system of equations. And if I want the original parabola, I just got to find a, b, and c. And if this says using an augmented matrix, I have to turn this into what? Which, by the way, I think you could probably go straight to the augmented matrix if you're kind of on your game, right? You probably don't have to write this. You could say, hey, if I plug a -2 in there, I get 4a. I plug a -2 in there, I get -2b. I plug a -2 in there, there's no place to plug in -2. Coefficient of c is 1, and then equal 5. So I could probably do that as I went. But if you needed to do it like this, knock yourself out. 64, 8, 1, 15. And if that is an augmented matrix, can you go through the Gaussian elimination process to make those 3 things zeros? Now, on my test, I will probably say, using Gaussian-Jordan elimination. With a calculator, what's a nice way to use Gaussian-Jordan elimination? Reduced row echelon form. So what we're going to do is probably do that. So we take out our calculator. We go menu, matrix, 5, left side of the book button, matrix button, tab down, 3 by 4. Get that in there, enter these numbers, 4, tab, -2, tab, 1, tab, 5, 16, 4, 1, -1, 64, 8, 1, 15. We hit enter, and it spits out 1, 0, 0.5, which is a half. Although if I need to make sure that's just not a bad rounding, then go and change it to fractions. And then 0, 1, 0, -2, and then 0, 0, 1, -1. So what does this mean? This is where people mess it up. What did I just find?
A, B, and C.
A, B, and C. I have people all the time that go X, Y, and Z. And I'm like, what the heck is X, Y, and Z? Especially Z, right? I'm trying to find what? A, B, C, so I can have my quadratic function, right? So the equation of the parabola. So this represents A is a half, B is -2, C is -1. So my equation is y equals 1/2 x squared minus 2x minus 1. And that is the parabola that goes through those 3 points. And that, sweet, easy way to get there. So, with that in mind, what about number 10? Can you use an augmented matrix and reduced row echelon form, same thing we basically just did, to determine the cubic equation? Now, what does a cubic equation mean? So that would be y equals ax cubed plus bx squared plus cx plus d. Now, obviously, if I have 1, 2, 3, 4 variables I got to find, A, B, C, D, I would need 4 equations, right? And sure enough, I can get 4 equations because I have 4 points. All right? So you saw that I needed 3 points for a quadratic that was squared. I needed 4 points for a cubic that was cubed. And if you look down at the next question, it says, how many points would you need to determine the equation of an nth degree polynomial this way? And what? Plus 1. Because right, I need 1 more point than the power. Why? Because when I write it out with powers, it always goes like power, 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 constant. The constant is 1, that you get 1 extra variable per power, right? With the squared to the first constant, that's 3. With the cube squared to the first power, constant, that's 4. So it's always 1 more than the degree. That's how many points I would need. And you see that right here. So what am I going to do? I'm basing everything off of ax cubed plus bx squared plus cx plus d equals y. Again, I like the y over there because that's how I've been doing RREF. So first thing, what are you going to do? And I'm going to go straight to my augmented matrix. So if I were to plug a -1 in there, what do I get? -1a, so -1. If I plug a -1 there, what do I get? 1b, so 1. If I plug a -1 there, I get -c, so -1. And then I plug it in there, and there's nothing to plug in, so the coefficient of d is always 1. And then what do I end up with as my constant? It's -16. So -16. And then I move to the 2. Right? When I move to the 2, what happens? So 2 in there gives me 8a, so 8. 2 in there, 4. 2 in there, 2. Nothing goes in with the d, so coefficient of 1, and you end up with an 8. 1 in there, 1, 1, 1, 1, -2. And then 3 in there, 27, 9, 3, 1, 36. There is my augmented matrix. I pull out my RREF. And it should I hope. Anybody have this done? Okay, so menu, matrix, 5, left side button, matrix, delete 4, tab, delete 5. Okay. Then -1, tab, 1 tab, -1 tab, 1 tab, -16. 8, 4, 2, 1, 8, 1, 1, 1, 1, 8, 2, 7, 9, 3, 1, 36. And it spits out 2, -3, 5, and 6. So those stand for what? Good. That's my A, my B, my C, my D. So back up to this, y equals 2x cubed, -3x squared, 5x minus 6. If you're not sure you're right, plug the point in there. Plug 2, 8 in there and see if that doesn't work. It will. Y'all with me? Isn't that nice? Now, we also have a program called a regression analyzer that will allow us to do a regression curve that goes through those points. So you can pick up, and we'll learn about that this year. In the future, we probably won't learn it in this class. We'll learn it in Algebra 2, because that's now Algebra 2 with statistics. That's new this year. You didn't have that last year, but that's the new course of study. It has to put stats in it. So we didn't learn last year, we'll learn it this year, but after that, we'll probably flip-flop.
So they don't learn trig.
Yeah, it's Algebra 2 with trig and statistics, but they call it Algebra 2 with statistics. So what I'll probably do is shove stats in there and move probability to this year. You guys had probability last year and then a quick review of probably this year. You guys will have to get on your horse because we'll be doing 3-day review. And it normally takes 10 days to go through. So you'll need to maybe encamp in here for a while. Make sure I don't, how would my father say it? Tear you a new one. Anyway, y'all with me? Probably don't want that video. It's all right? It's my last hurrah. Are we good on this? Okay, I think that's all I have. So if you can do the work on this, I think you're in pretty good shape. Remember, leave yourself some breadcrumbs, a little trail back to reviewing, since you're not going to have a review sheet. Stuff that you miss on any homework problem, I'd be putting like a red star or something, and I can go back and review those to make sure I'm in a good place. All right.